Thanks. So the talk that I'm going to give you today is a talk that I gave at a workshop this summer at the NAACL conference in Montreal. And the directive I was given for that workshop was to be controversial, not to have any fully formed results or new theory or new experiments or anything. So this talk doesn't have any of those things. It's merely controversial. It's only meant to get you thinking. And maybe get some ideas flowing. The main thing that, I'm not even going to tell you what workshop I was speaking at, you can probably figure that out. But the main thing that I decided to talk about is one thing that has kept me awake at night for a long time, which is how do we evaluate a computational model of natural language text? How do we know when we have a good model? So I want to start out, I guess I'll acknowledge a few people who influenced my thinking on this. Some of them are in this room. And I'm just going to sort of start out for this audience by saying a little bit about how we build natural language processing systems. So a natural language processing system takes some text and converts it into some deeper representation that's useful, right? That's useful for answering questions, or maybe translation into another language, or maybe extracting structured information out of the text. There are a lot of things that natural language processing might be useful for. Let's just take it for granted that it's useful and say, how are we going to go about building such a system? And so, there are really three options at a very high level. One is the way that people did this until, say, the early 1990s, which was to sit down, write down rules reflecting on how you think you turn text into a deeper representation, and use those rules, apply them to data, and that's your system. That pretty much went out of fashion with the rise of machine learning, and so the second paradigm, and the dominant one today, is you sit down and you annotate some data, or you get some of your friends who are experts at reading text and transforming it into structured representation, and you annotate manually some examples, and then you apply supervised learning to learn the transformation from input text to that deeper structure. That's pretty common now. And if you've seen talks about NLP, you've likely seen somebody talking about that kind of supervised approach. Recently, I would say in the past 10 years, there's been a lot of interest in doing this kind of thing without fully annotated data, either with partial annotations, or a little bit of annotated data and a larger pool of unannotated data, or just unannotated data and completely unsupervised. Infer the structure of your natural language text so that you can use your model downstream. And so I mainly want to say that number 3 is a really rich research topic right now. A lot of people, both at CMU and sort of around the world, are really excited about the idea that you can take text and maybe just a little bit of annotation or a little bit of declarative knowledge and do something, probably involving some machine learning, and then get back an NLP system that actually works. And this research topic has actually, there's been a lot going on in the past few years. There are connections to theory of computation, cognitive science, learning theory. It's a really exciting research area. And people have developed a lot of really elegant, beautiful models that are very clever in the ways that they exploit data, incomplete data, to infer linguistic structure. So that's a big research topic right now. But the thing that keeps me up at night, full disclosure, I do a lot of work in number 3. But the thing that keeps me awake a lot of the time is how we evaluate those kinds of unsupervised systems. So there are a few things that are annoying. One is that we really don't have anything more than a kind of intuitive, community-wide consensus of what it means to be really unsupervised. Right? People put all kinds of different kinds of information into their systems and use different kinds of resources and data, and it's really not exactly clear where the line is crossed between being semi-supervised or unsupervised. And I'm not sure how important that is. It just creates difficulty when people are reviewing your paper and they disagree with you about whether what you've done is actually unsupervised. The bigger issue, I think, is that usually the way I'll talk in a minute about how we usually evaluate these things intrinsically. But the problem is that the way we do it, most people don't actually respect, except people working on the problem you're working on. So we have these sort of bake-off type tasks, and the evaluation criteria are, let's just say, they're not widely accepted. Finally, even when we choose, and part of the reason I guess that people don't respect those kinds of evaluation is that when we go about doing these sorts of evaluation, we're often using data sets that are fairly unrealistic. I guess the way to talk about this is to say that we've been using some of the same data sets for nearly 20 years. And the decisions that were made when those data sets were constructed are often taken to be ground truth with an almost religious fervor. But in fact, there were a lot of sort of seemingly arbitrary decisions made about how to annotate those data sets. So I think we should be somewhat skeptical of whether the data sets we have are really linguistically appropriate or practically realistic. Okay, so I should get a little bit more concrete. Let's talk about how do we evaluate these kinds of systems, these sort of unsupervised or less than supervised NLP systems today. So this schematic sort of explains my view of the sort of standard paradigm, which I'm going to call match linguists. So here's the story. We have some source of data, the world, right? There's P star, some distribution over instances X. X gets generated, and then X goes to a linguist or an annotator who's an expert. And that expert is going to create Y star, the true annotation of X. So if you want to be really concrete about this, think of X as a sentence in English, and think of Y as its parse tree, right? Its syntax. And so if you have a smart linguist, they can look at any sentence in the language, and they can give you back its parse tree. Meanwhile, what I want to build is what I'll call a linguist in a box, or as Jeff Gordon calls it, a linguist in a box. Some people call it what would a linguistics professor do? And I'm going to simulate this linguist by building a computer program that turns X into Y, which is my guess as to what the linguistic structure is. Right? So this should look very familiar if you're a machine learning person. You've got the true answer, you've got the machine's answer, you check whether they match, and you get a score. Right, and maybe we have some soft matching criterion because we know it's really hard to get the whole parse right. Maybe we're going to be really strict and say you only get a point if they're the same. Exactly, right? There are lots of variations on this theme. I'm gonna call my linguist in a box Claude for the purposes of this talk because it's just convenient to give it a name. Does this make sense? Right. So this is sort of the standard thing. My linguistics professor, by the way, is Indiana Jones. People don't remember that he was a linguistics professor. He spoke a lot of languages. So this isn't, there are some problems with this. So the first thing is that linguists, like Indiana Jones, are not cheap. And so we don't usually hire one to give us Y star for new data very often, right? This is the problem I talked about before. We typically had that guy, we hired him back in the 90s, and he gave us a data set, and we've been using it ever since. Right, and you can point to examples of this for a wide range of natural language processing tasks where a standard data set was fixed at one point in time and we continue to use it. And that means that we're stuck with the choices that were made when we asked Professor Jones to do his job. Right, so if the level of description were to evolve, if we had a different theory of language, we'd have to go hire another linguist and start there. And we only have the data that they chose to annotate. So in the case of syntax, the standard data set is the Penn Tree Bank, which for God knows what reason was annotations of 1980s Wall Street Journal articles. So it's like Reagan-era drivel about whatever. It's very, very politically one-sided and certain strange kind of stylistically language. So in any case, this is kind of how it works, and then so the next thing you should see is that if I build a system and somebody else builds a system, so call my system Claude, call Brian's system Chloe. If we wanted to compete, we could put Claude and Chloe in sort of the same simulation box with the same data, and then compare their matching scores, right? And if I did significantly better, if Claude did significantly better, then I win. So that's nice, right? We like being able to evaluate automatically using simple comparisons. So this is another kind of evaluation that people don't use very much these days, but it does have some nice properties. It doesn't require a linguist. So we have our data, and our data goes to Claude, and instead of giving some kind of prediction of structure, maybe Claude has some model of structure, but it's not really important what Claude believes about the structure of this sentence X. Claude is just going to give me back a number, the negative log probability of X. Okay, right? So this is sort of like how many bits does it take Claude to, on average, encode this piece of data. And if Claude gives me an honest answer and doesn't cheat, then I can take a geometric mean over a bunch of instances and I can get back a perplexity score from Claude. Which is just sort of saying how surprised is Claude, how perplexed is Claude at this data? And the lower he gets, the better. Right? The more probability he assigns to this new data that he hasn't seen before, the better. Now, if I want to go into competition mode and compare Claude with Chloe, then we've got to agree on some things. We've got to agree on the vocabulary. That's very important. Otherwise the numbers don't come out comparable. And agreeing on the vocabulary for many languages is quite difficult, right? In English, we can sort of say, well, maybe there are 30,000 words, and anything else we're just going to call an unknown symbol. If you try doing that for a language like Turkish or Malagasy, where words themselves have internal structure and you can generate new words much more easily than you can in English, then this is going to be more difficult. Not completely impossible, just more complicated. The other thing is that this value for today's models of structure, this value is actually sharp P hard to complete. Right? It involves, basically it involves calculating some kind of partition function like number. And so usually people have to use approximations. And it's a slippery slope because if you want to calculate the probability of your data under your model and you have to approximate, you get to choose your approximation. And maybe you just always happen to choose an approximation that is biased favorably towards your system. Right? So what we really want is, if we're going to do this, we really want to make sure everybody's competing the same way and using the same kinds of approximations. It's for reasons like these that this is not a very popular way of evaluating models, although you do occasionally see it in literature relating to text data. Okay, so here's something that pretty much everybody agrees is a good idea. So if you have some external system that uses structures like Y, right? So Y is a parse tree, and maybe you have a machine translation system that uses parse trees. That's great, right? So you can basically run everything through and see how well your downstream system works. Does it get better if you use Claude versus Chloe, right? And so if Claude's a better parser, then we would expect that the system score, whatever it is, the machine translation scores would get better. I don't know, what do you think about this? Yeah.
How do you evaluate the system?
Yeah, exactly. So you're basically just passing the buck. You're assuming that those guys who build applications really know how to evaluate their applications, which is something you should be skeptical of. There's a lot of controversy about how you should evaluate a machine translation system or a question answering system. I mean, I guess there's some obvious cases where it's clear that it works. Like if your system wins Jeopardy, then clearly it won, right? But we don't have these kinds of runoff competitions all the time. Okay, so those are sort of the three main options today for evaluating NLP systems. One of my sort of issues with this is, one thing is that I think P star, this sort of idea that there's a single true distribution over text, is a gross oversimplification. Anyone who knows about language will tell you that there's sort of a lot of things that affect what language looks like. If I were tweeting this talk instead of giving it in an academic setting, it would look a lot different, right? So I think what we should actually be thinking about is what the distribution is of our data, of our linguistic data, given some metadata that's relevant to the situation or relevant to the experimental question we want to answer. I think also that what this sort of settings we're using now are ignoring is the fact that we have tremendous amounts of data, virtually unlimited amounts of text, in a wide range of contexts with a wide range of kinds of metadata that maybe we should be using if we want to build real models of language that are more useful for real data. And I actually think that curating that data and building interesting data sets that are relevant to a particular context is good research and should actually get credit in this system. Right now it doesn't. Right now that role is sort of just taken for granted. So I'll come back to that in a little bit. I'm now gonna put forward kind of the main idea of the talk, which is a different kind of evaluation that separates out some roles. So this is actually building on a famous example of an indistinguishability test from Turing. People remember the Turing test? I'm not going to go over the Turing test. Indistinguishability is still sort of important to our evaluations. Usually we think of indistinguishability in terms of, is this system's output indistinguishable from this other system's output? But I think what we can do is we can actually tease apart a couple of different roles and then perform a slightly different kind of indistinguishability test. So here's the adversarial evaluation, the basic idea I'm going to propose. So we have our data X, just like before. It maybe comes with some metadata. And we pass the X and its context, its metadata, over to a different player who we'll call Zelig. And Zelig's job is to produce another piece of data that we'll call it Z. So if X is a sentence, Z is also a sentence, right? So Z is of the same kind as X. And then what's going to happen is we're going to randomly permute these two and ask Claude to distinguish between them. Can Claude tell which is the true one and which is the contrived one that came from Zelig? And so Claude gives an answer Y based on whatever model Claude wants. Claude can have a parser, semantic analyzer, whatever Claude needs, right? However your theory works. And Claude produces which one he thinks is wrong. And then we check. Did Claude get it right? Did Claude pick Z or did Claude pick X? If Claude made the right choice, then Claude gets a point. Right, so Claude's goal is to accurately tell true data from fake data. And Zelig's goal is to take true data and corrupt it in a way that is believably still language and trick Claude. I'll leave that up for a second, see if people understand. Yeah.
So Claude was just a second ago producing parse trees, and now he's
producing bits.
Now he's producing bits.
So one possibility is that Claude ought to use a parse tree to make his decision. So suppose Zelig were really naive, right? We all know, none of us would ever build this Zelig, but here's a dumb Zelig you could build. Zelig could randomly pick any word in the sentence and delete it. And one way you might be able to tell whether, or let's say replace it with another word. Right? And one way that you might be able to tell that had corrupted the sentence would be to try to parse it. And maybe your parser would fail or give a lower score. Yeah?
Can you give a concrete example? So you said deleting or permuting a word, but like you can also think of like substituting a word with semantically the same word.
Sure. So you've just come up with a more difficult Zelig, right? And so I would need a more complex Claude to try and determine the difference between the two.
But is that always possible?
It's a great question, right? The only way you're going to be able to tell is if you actually build it, and nobody can build a Claude that can tell. Right? So now Zelig is a research problem, right? Both of them are valid research paths, and things you could try to do to show that you had demonstrated that you had a good model of language. Yeah.
So is this really similar to contrastive estimation?
I can't say that they're not intellectually related. Yeah.
Okay.
I'm not going to talk about that today, though.
Okay.
Okay, so if I want to compete with, say, if I'm going to let Matt build a system called Chloe, and I'm going to compete, and my Claude is going to compete with his Chloe, here's how a competition would work. We have a set of unordered pairs, X and Z, and each of us is going to guess which one is wrong independently, separately. And so if we've been given Zelig, who's been corrupting the data and producing the Z, and then we can calculate our matching scores. Here's an interesting kind of extension. If instead of just giving one example, Zelig actually gives the entire set of all possible strings. And so now, basically what happens is that Claude gets sigma star, and Claude has to assign scores to everything in sigma star, and then bet proportionally, then what we've got is perplexity. Right? If we introduce this notion of proportional betting. But I think it's a lot easier to just think in terms of a binary decision by Claude. There's a lot of things in between, obviously, but I think the key point still comes across if we say Claude is just making a decision between a true piece of data and a corrupted piece of data. Okay, so here are some good things about this kind of evaluation. One, it's totally objective. We don't need any annotators. We just need people to build systems. We're good at building systems. We're bad at annotation. It's very easy to share results. If we agree on a data source and Zelig a Claude, and you want to reuse any part of that, then I can provide you with my tuples x, y, z. If we add some context variables to the x's, if we have metadata, then that might allow us some really nice ways to do statistical error analysis, where we relate mistakes to different features of the data, something we don't usually do in NLP. One really important thing is that you don't have to be a probability person to do this, right? You don't have to build a probabilistic model of the data. You just need a program that can decide which of two strings is the right one. So that opens the door for a lot more people who aren't as good at working with probability models or who don't believe in them to play on the same terms. And finally, I think this is really important because the field of natural language processing does tend to fragment over theories of language. Nobody has to agree on a theory, right? The task is sort of external to all the theories and all the representations. You can use whatever you like. The question is, do you do well at making this binary choice? And you can apply your theory however you like to making that choice, or to generating corrupted versions of the data. So that leads me to Zelig. It's really kind of important to think about what sort of operations are going to work here and lead us to build good models. Yeah.
So the model which decides which one is the correct one will not use probability?
He could, but he doesn't have to.
Okay.
Your advisor won't let you do anything else.
No, you said because you don't need to know probability.
You don't. No, you can make a decision without using a probabilistic model. Right. You could have a decision tree.
Okay.
So I could just make a Zelig that returns the last sentence.
You could.
So then what?
So then what would probably happen would be no Claude would ever do better than chance, right? And then you would have failed. Right, we have to have certain criterion for being able to trick Claude a certain number of times before it's a worthwhile Zelig, right? I mean, you certainly would. That would be a very interesting paper to write. The results wouldn't tell us anything new, so probably nobody would care. Great. Okay, so let's talk a little bit about Zelig. Do people remember this movie, Zelig? This was a great it's a great Woody Allen movie. This is Woody Allen with Herbert Hoover, the president. It was this movie where the character Zelig just sort of, he like blended in everywhere, and they just like stick him in all these different places in history. And it's always Woody Allen. It's a really funny movie. Anyway, so Zelig could be, the way I think about Zelig is a linguist who has some kind of theory of language, and Zelig does what linguists do really well. I don't know if people have taken linguistics classes or know, are there any, apart from Chris, are there any linguists? No? Okay, tell me if I'm wrong. Linguists love to take a perfectly well-formed sentence and then find a way to break it so that it has a star in front of it. That's like 80% of what I did in linguistics class, right? You find sort of what exactly are the distinctions between a grammatical version of a sentence and a degraded version of a sentence that just doesn't sound right. So operationalize that into a program, please. And we'll call that Zelig. And now it's a system, and so Zelig can play the game. And if you've got a good theory and you can consistently trick Claude, then you've done something good, and then Claude has to get better. Okay, so interestingly, we now have a competition between two different Zeligs, or let's call them Zelig and Zelda. So some theories of language are going to explain why X is good and Z is bad, and others might not do as well. And so this is sort of a different kind of linguist in a box. This is a linguist who takes good sentences and does bad things to them, and finds transformations that make them, putting a star in front of a sentence is just a linguist's way of marking that it's bad, that it's not grammatical. So how do we know if Zelig is better than Zelda?
Claude makes one mistake.
Exactly. Yeah, we use Claude. So they agree on Zelig and Zelda agree on a Claude. We clone Claude, and then we subject Claude 1 to pairs X and Z where Z comes from Zelig. We subject Claude 2 to pairs X and Z such that Z comes from Zelda. And then Zelig wins if Claude 2 does better than Claude 1. So we use the same scoring mechanism and do a controlled experiment, Zelig against Zelda. So we can use the same framework to compare are to do a different kind of competition. Now, interestingly, I'm going to claim that some things we already do have the feel of a Zelig-Zelda competition. Let's just call it a Z competition. So machine translation, for example, is a lot like this. So in machine translation, X is a pair. It's two sentences. XS, a source sentence, and XT, a target sentence. And Zelig is a translator who takes XS and translates it into Z sub T. Okay, and then we say to Zelig, here's X sub S, here's the source sentence. Then we say to Claude, which one of these two is the machine translation? Right, so this would be one way to carry out a machine translation evaluation, to show a system, an external system, both the machine output and the human output, which is X sub T, machine output is Z sub T. And then we say, if Zelig gets a lower S, if Zelig manages to confuse the human or the Claude, if it's a system more often, then Zelig wins. This is sort of one way you might think about doing a machine translation. Does this make sense, or is it too many variables to make things floating around? Is this kind of, Chris, do people do this for the WMT evaluations? They do something like this.
Yeah, it's not completely far off.
But Claude's a human.
Claude's a human.
Or a bunch of humans. Right? Usually students. Another one you might do is a question answering might be seen as a Z competition. Almost the same thing, right? You have a question answer pair. Answer Zelig is going to give an answer. Is going to answer X sub Q and give Z sub A, and usually Zelig doesn't get to see XQ. That's kind of the important thing here. It only gets to see XQ, doesn't get to see the true answer. Otherwise, it wouldn't really be a question answering system. And so what we're really doing is we're evaluating Zelig for being able to produce good answers. And then we have some output, some human or system which tries to tell which is the machine answer. And you do better if you trick that system, if you're not distinguishable. And you can do better if you have many Claudes, right? Many humans or many systems that are designed to try and tell machine output from human output. Okay, so that's the high level idea. You might wonder, I don't think people in this room are likely to fixate on this question as much as my initial audience, but you could ask, is this supervised or semi-supervised or unsupervised? And the answer is I haven't told you. All I've talked about is test time. I've only talked about the evaluation. So what you could do, if you wanted to make this kind of a supervised setup, you could let Claude observe XZ pairs and tell him which one is X and Z and let him train for a while before you run testing. Or Zelig could get to observe interactions with Claude before he has to actually start testing. Right, so you could set it up in a supervised setting where they get to observe each other for a while, or you could do it completely unsupervised and assume that the models are built offline before you run the evaluation. Yeah.
So some slides ago you said this is an objective way of evaluating. What do you mean by that? Like, doesn't it depend on the Zelig, Zelda versus? So you can't agree upon one of the Z's. So why is this an objective way to evaluate? So if system A does well according to Zelig and bad according to Zelda.
It's conditioned on Zelig. It's an objective way to evaluate Claude versus Chloe. Conditioned on Claude, it's an objective way to evaluate Zelig versus Zelda.
But it's not objective. It's conditionally objective.
Well, there's no human subjectivity coming in.
Which system is better? Like if I do well on Zelig and bad on Zelda versus the other way, and some other system does the other way, which one is better?
Oh, I see your point. So then the interesting question is what differentiated Zelig and Zelda, and what does that tell you about the properties of either the data that was involved or the systems that were competing, right? And so by knowing exactly, by controlling exactly what Zelig and Zelda are, hopefully that gives you a better window into what works and doesn't. Right, so remember at the end of the day, we're not just trying to get better numbers. We're trying to understand what works. That would be kind of my high level. Yeah.
I think to relate to that question, my feeling is that maybe you pretend saying you don't need a theory anymore, but the point is that certainly it's cheaper. So it's cheaper probably for you to build a Zelig than to hire particularly Harrison Ford and say for a speech tax or something.
Right.
But when you write your Zelig, you are encoding.
Oh, absolutely. Everybody's not, no. I didn't mean to say there's no theory. I meant to say that there's not, everybody who's playing the game doesn't have to agree on the theory. And in fact, different theories can compete within the game without, you know, there's no, we don't have to agree on a representation, we don't have to agree on the transformations. That's all inside of each box individually. So everybody's going to have a theory, but they don't all have to have the same one.
But then you make analogous to saying we're trying to learn how to parse dependency structures or tree structures, for example.
Yeah.
And
Yeah, so two different systems could have, you know, Zelling could be operating on one and Claude on another, and that would be fine. Okay, so let's kind of move on. I want to talk about the last thing I want to talk about briefly before I run out of time is there's a twist. So there's one more thing I'm going to add to this, which is another player. And so this is sort of thinking about the data. So one possible objection or maybe frustration with what I proposed is that now the linguists are gone, right? I don't have annotated data anymore. I'm not relying on linguists to give me a gold standard, which many people see as a benefit, many people see as kind of a disadvantage, especially if you're a linguist. So I'm going to put forward that the way we treat linguists now is actually kind of unfair, right? So basically all we want from them is more data, more complete annotations, do it faster, be consistent, and basically give me all the annotations that you can as quickly as you can and as cheaply as you can. But actually I think what we're doing is we're misusing their effort. Oh right, and we don't even know if they're doing a good job, we just sort of assume that they're doing a good job if they get good kappa scores, if they agree with each other. Right, so we sort of put them on a pedestal, we treat them like God if their kappa scores are high enough, and we treat their output as gold standard, and we don't worry about it beyond that. But actually, I think there's a more interesting role for linguists to play in these kinds of evaluations. So here's my proposition. Instead of assuming that we have some magical E-star distribution over X, let's put another player in, call him John, and let John curate or choose the data. So John could be a programmer, could be a human. My thinking initially is that it's just an algorithm that selects instances from our practically infinite pool of data. So one John could be take the 37th sentence in the New York Times each morning, right, and just send it into the stream. And there are different variations on this and how much is revealed as far as where the data come from. I think the metadata are particularly interesting. So if John is a linguist who happens to be particularly interested in certain phenomena, say, I don't know, conjunctions, then John might go looking for sentences with conjunctions and try to generate an interesting pool of data that shows a variety of phenomena relating to conjunctions. And maybe give some metadata so that later on we can do error analysis of the systems and see where our models do well with this phenomenon and where they don't. Okay, so metadata could be things like what website did you get this sentence from, when did you find it, what language is it in, other metadata. Could also be annotation. It could be things that humans annotate, like this is a conjunction of two things that are both nouns, or this is a conjunction of two things that are both verbs. It could be done automatically. It could be some kind of pre-processing. There are lots of things you could imagine happening in the annotation stage. But my sort of conjecture is that if we did a better job of labeling our data just at this sort of coarse level with a little bit of metadata for key phenomena that we think are important for language, then we might get something more useful for computational linguistics. Okay, so what that means is that linguists would be moving more toward, there's a lot of work now in trying to move linguistic knowledge into sort of a more declarative form, like writing down a prior or some constraints or some basic rules that are expected to hold most of the time, maybe treated as pseudo-observations. These are very common themes now in unsupervised NLP. Maybe now what we should do is say, have linguists declare things about examples. So here's a sentence, and they can say, oh, this has a relative clause, right? Or, oh, I think there's some interesting attachment ambiguity here, right? Linguists can find all kinds of interesting things to say about sentences, and so those declarative things might lead us to a much more useful data set for understanding the errors that systems make. particularly if we can pass large amounts of data through our Z and C competitions. So, okay, so the last thing is that we can actually have competitions at the level of J. So don't try to read this, there are too many subscripts. John and Jennifer are going to play the role of the data generator, the data source, and they're going to agree on a Zelig and a Claude. Maybe there's a suite of them. But then we have to clone Zelig and Claude, and then we run the competition with John generating the data over here, Zelig 1 and Claude 1 are working with that data, and then Jennifer generates data over here, and Zelig 2 and Claude 2 are generating data there, and they both go through the pairs, and basically at the end of the day, John wins if Claude 2 wins, right? John has managed to transmit good data past the Zelig, who's working adversarially against him, to Claude 1, who's managed to do a better job than Claude 2, or sorry, other way around. Did I get it backwards?
Yeah.
I did, yeah. So if Claude 1 wins, then John wins, other way. So if John has made Zelig 1's task harder, then John wins. Okay. So now we've turned everybody into a competitor. So just a few, before I run out of time, just a few more thoughts. If there's collusion, then I don't know what happens. It could get very complicated, and I'm not sure what to do with that. I think probably the right thing is to think about everybody kind of working independently and nobody colludes. You only get to play one role. People are tempted and have suggested that I think about a game theoretic analysis of this, and I think that might be interesting, but I don't know how to do it. So if you think that this kind of setting needs that kind of analysis, then come talk to me and tell me how to do it. A couple of people I talked to when I presented this work before, one person was particularly concerned that we might just build Claudes and Zeligs and Claudes and Zeligs, and we wouldn't really get anywhere. It wouldn't actually benefit any downstream application because we'd just be sort of chasing its tail. And I think that's a legitimate worry, and I think that part of I don't know that we're not already doing that, right? So I'm not sure that that's going to really be a change in the current state of affairs. But I do think that if we keep some extrinsic evaluations in the loop, then that's less likely to come about. Another question, and I don't really know the answer to this, is whether the whole thing can be gamed, whether there are ways to just sort of try to win by cheating. I don't know. I'm not sure what the answer to that is. Probably, but I'm not sure if they're worth worrying about. So I'll close by telling you who I named these after, people who did really useful and interesting work, and are dead now. Any questions? Yeah.